sidebar, point out some facts that you need to know. As we're working as you're working redox reactions, you have to be able to identify what's being reduced and what's being oxidized. And I'll talk about that momentarily if you don't know what those terms mean. So oxidation number, we really apply only to molecular substances or atoms within molecules. And remember, polyatomic ions, perhaps you don't know this already, polyatomic ions are covalently bound species that behave and react as single ions. So if we're looking at oxygen within sulfate, for example, we have to determine what the oxidation number of sulfur and oxygen is within that sulfate, even though sulfate is a polyatomic ion. Charge we reserve for ionic substances. But for our purposes in reduction oxidation reactions, we're going to use these terms interchangeably for the most part. This is one of the steadfast rules of redox. Oxygen is always -2. Since I've been up for over 9 hours and logged 4 miles running this morning, yes, I'm a little loopy, so I even color-coded it for you. I don't have anything cutesy for hydrogen, but hydrogen is generally going to be +1 in terms of its charge or oxidation number. If it's an ion, then whatever the charge of the ion is, that's the charge. Right, look at the charge. If it's an element or a molecule,
So if
it's an element or a neutral molecule, or a gas or a liquid, it's going to have So one of the examples that you'll work today is permanganate. You'll need to know what the oxidation number is of the manganese within the permanganate ion. 1 manganese and 4 oxygens together, added together, give a total charge of -1. We know that the 4 oxygens have to be what?
-2.
That would be 1 oxygen.
Oh.
4 oxygens have to be
-8.
-8. And so whatever manganese's charge is added to this -8 gives a final sum of -1. So manganese in the permanganate ion has a charge of +7. And again, you use that fact that oxygen is always -2 to make that determination. Most polyatomic ions contain oxygen or hydrogen. If they do not, then you have to rely on your knowledge of the periodic table and what the most common charges of the elements are based on their location on the periodic table. For those who weren't here yesterday, I'm going to go through this relatively quickly. You might want to get the non-drowsy notes from someone later on. But the term reduction refers to any species in a system whose oxidation number or charge lessens. And it lessens because it becomes more negative by gaining electrons. The only way oxidation numbers or charges can change is through the loss or gain of electrons. Protons are never involved in any type of chemical reaction in terms of exchanging, because protons are bound to the nuclei of the atoms in that system. You can't just arbitrarily add protons or remove neutrons from atoms, then they become something else. So the only way to manipulate oxidation number or charge, and notice how I'm using those terms interchangeably, is by the addition of electrons. Oxidation means that you have a species that has an increase in its oxidation number or charge, and that happens when it loses electrons. So if we look at the group 1 metals that as atoms, as neutral atoms, have charges of 0, they will readily give up an electron and form ions of a +1 charge. So going back to the question that I posed at the beginning of class, the group 1 metals will oxidize very easily. Some will oxidize just simply by exposing them to the air and the water vapor in the air. Every single displacement reaction is a redox reaction. Many double displacement reactions are redox reactions. And then there are a multitude of reactions that don't fit neatly into one of those categories that are still redox reactions. And the way you tell whether or not it's a redox reaction is by looking at the charges or oxidation numbers of all species on the reactant side and product side. And if one thing changes, then it's a redox reaction. You cannot have reduction without oxidation. So if you see that one thing has changed, something else must have changed as well. So as we look at this first example, we can see that cerium 4+ ions, notice that the anion is irrelevant. We're looking solely at net ionic equations now. Cerium 4+ reacts with 10 2+ ions, again, regardless of the anion. And as products, we end up with cerium 3+ ions and 10 4+ ions. Doesn't get much more basic than this. In this reaction, the cerium is reduced. And you know that because its oxidation number, or charge, lessens. It gains an electron. 10, on the other hand, is oxidized. It starts out as 10 2+, and it ends up as 10 4+. So it has to lose electrons, hence it is oxidized. To balance this reaction, again, you can't just change coefficients, because looking at it right now, everything is balanced in terms of numbers of atoms. We have to balance it in terms of what's happening to the change in charges among the cerium and 10 ions in this system. So the methodology we use is called the half reaction method. We identify what's being reduced, and we focus just on balancing that half reaction. We set it aside, and then we look at the oxidation component of the system, and we balance that half reaction. And then we add the two half reactions together to get our complete, balanced redox reaction. You can start with the oxidation if you want. So the reduction half reaction involves the cerium. And the cerium is being reduced from cerium 4+ to cerium 3+. Now, the only way for cerium to be reduced from 4+ to 3+ is if it gains an electron. So in order to end up with cerium 3+ as a product, we have to add an electron to that cerium 4+. And in terms of balancing that half reaction, now it's balanced. If I add up the total charges on the reactant side, what do I get? Plus what? 3. And then on the product side, it's also plus 3. And I have the same number of cerium ions on both sides. Okay, so I'm done with that for right now. So now I'm going to look at the oxidation half reaction, which involves 10 2+ being oxidized to 10 4+. For 10 2+ to increase its charge by a magnitude of 2, what has to happen?
You have to take away 2 electrons.
It has to give away 2 electrons. So for every 10-4 ion that forms, every 10-2+ ion has to give up 2 electrons. Again, we look at the charges. Over here it's +2, +4, -2. It's +2 on that side as well. The charges don't have to equal 0, but they have to be equal on both sides. Alright, so that oxidation half reaction is balanced. Now, I have to add these 2 half reactions together. And the stipulation is, when I'm through adding them together, I can't have any electrons left over. So I have to multiply one or both half reactions by some whole number in order to get rid of or cancel out the electron. And in this case, I'm multiplying the reduction half reaction by 2 so that I have 2 electrons on the reactant side, 2 electrons on the product side, and then I can add them together. This 2, however, multiplies through. So that gives me 2 electrons plus 2 cerium 4 plus ions, yielding 2 cerium 3 plus ions. In other words, it takes 2 cerium 4 plus ions in order to give or donate those 2 electrons that are needed to oxidize the tin. Lastly, I'm going to add these 2 half reactions together. Notice that the electrons cancel out, and so I'm left with 2 cerium 2 plus, or rather 4 plus, ions plus 10 2 plus ions, yielding 2 cerium 3 plus ions and 1 10 4 plus ion. So this would be the final answer. So again, what makes it more complicated is the fact that you have to account for where those electrons are coming from that both reduce and oxidize those species in that reaction. Yes, it was balanced initially up here in terms of numbers of atoms, but remember, we're trying to describe the chemistry of what's happening. This isn't Chem 1 anymore. We're not just trying to balance equations and make things happy and check off something on a checklist. We want to understand it at the atomic level, at the molecular level, and understand why you need twice as much cerium reacting in order to oxidize that tin. And the reason for it is when the cerium ions are reduced, they only give up a single electron at a time. So we need twice as much cerium reacting to give us double the number of electrons available in order to oxidize that tin. All right. Now, yes.
So basically, with the electrons, you need to make sure that they balance out if you're adding something on this side and subtracting something on the other side?
Yes.
Okay.
And I should have double checked as far as charges. On the product side here, I have plus 8 and plus 2, so that's plus 10. And on the product side over here, I have plus 6 and a plus 4. So that also gives us plus 10. So the charges, the atoms, the charges have to be equivalent, and we have to be sure that we're left with no electrons in our final balanced equation. All right, the next oftentimes you're going to see that a reaction is occurring in acidic solution. So the next example we're going to look at is this one, which is occurring in acidic solution. And remember, by definition, an acid or an acidic solution is one in which we have hydrogen ions available. We are going to, as this one is more involved, we are going to have to add hydrogen and water in order to balance this equation. Because if you notice, permanganate is a reactant, and there is nothing with oxygen on the product side. So to balance the oxygen, we're going to add water. This is all happening in acidic solution. Water is the solvent, so it's okay to add water. To balance the hydrogen, we're going to add hydrogen ion. Not hydrogen gas, but hydrogen ion. So the methodology is still the same. We still have to identify what's being oxidized, what's being reduced. We're going to break it down into two half reactions, doing the reduction half reaction first, and then the oxidation half reaction, adding oxygen in the form of water and adding hydrogen in the form of hydrogen ion. So, with that said, those of you who weren't here yesterday or who may not have completed this problem, let's work what we can using the previous example, but understanding that we're adding a little bit more to it now. It's a little more involved.